Welcome to the structure analysis class. So up to last class we have discussed about the slopes and deflections of a beam or in a portal beam how to calculate. So we have seen there are broadly there are two types of methods to find it out the slopes and deflections. First one is geometric method and next one is energy method. So again in the geometric method we saw there are multiple methods are there. One was double integration method, direct, then moment area method, and then lastly we discussed about the conjugate beam method. And similarly, we have discussed the energy method also, that is Castigliano's theorem we have discussed in details. And if you recall, all the structures till now we have discussed are actually determinant structure. That is, we can calculate or we can analyze the structure using the equilibrium of equations. Already we know that in 2D structure there are three equilibrium of equations, that is summation of all horizontal forces equal to 0, summation of all vertical forces equal to 0, and summation of all the moments about any particular moment should be 0 equal to 0. So using these three equations, till now we are analyzing the structures, and that too we have analyzed a simple structure. But in reality, if you look into your and the around, you will find all the structures are not in a small scale. It are large structures, and multiple bays will be available. So what is bays I am talking? So for example, if you see, we have discussed till now is a simple portal frame. Maybe this is call it one bay portal frame. But in reality, if you see, we have multiple bays. So this is one bay, next bay, third bay. If you look into our FST campus, so you will find so many columns will be there, and the beams are actually continuous. So if you see, this beam is a single beam, it is continuous beams. Whereas whatever we discussed till now up to lecture, before lectures, that was we considered only a single bay beam, and that too the structure is determinant structure. That means only using the three equilibrium of equations we can solve the structure. Solve in the sense we can compute the that bending moment diagram, shear force diagram, slopes and deflections. But in reality, all the maximum structures are actually, or maximum beams are actually continuous beams. So beams are continuing from one bay to another bay. So this induces the structure as an indeterminate structure. So let's discuss more about the determinacy and indeterminacy. So here in this problem, we'll discuss three moment equation to calculate the indeterminate structure. So as we already understood what is determinant and what is indeterminate. So till now we discussed a simple beam of having one hand is hinge, another hand is roller, right? So this type of beams we are solving, or maybe a cantilever beam. So this is a cantilever beam, right? Forces are acting at the tip. So these are the simple beams and all the determinant beams, like, because why, if you take reactions, total how many reactions are there? 1, 2 and 3. So this structure has actually three unknown reactions. So here you have two unknown reaction, and in this support you have one unknown reaction. So total three unknown reactions, and we have three equilibrium of equation also. So easily we can compute all the reaction forces, and we can draw the bending moment and the shear force diagram. We can calculate the slopes and deflections after application of the load. Everything we can do it within this simple structure. Similarly for cantilever beam also, it is also a determinant structure, because it is unknown reaction. Here it is 3, and we have three equilibrium of equations. So this is also a determinant structure. So using this any cantilever beam, we can calculate the shear force, bending moment diagram, shear force diagram, slopes, deflections, anything we can do. But in reality, if you look into, if you see any bridges or any structure, big buildings, multi-story structures, 10-story, 20-story buildings, there the structures are not that much simple. The structures are complex in the sense the beams are not single beam. There will be that, as I mentioned, the beam will be continuous from one support to another support. Maybe the loading condition also may be very much different. So till now we discussed very simple loading, a UDL or maybe a point load, but in reality the loading may be very much different, whatever we discuss in this course. So in that structure, how will you analyze? So that is our next question. If a structure is indeterminate, for example, if you take this simple supported beam, instead of this end is a roller, if this end is also a hinge end, then in that case you have two, and in this support also you have two unknowns. So total you have now four unknowns, and you have three equilibrium of equation, right? So maximum using the equilibrium equation we can calculate three unknowns, but still one more unknown we have to compute, right? So using normal method we can't do indeterminate structures. So this beam, if this end is hinge and this end is also hinge, then we call it this is a indeterminate beam of a degree of indeterminacy 1, because three unknowns we can calculate but one unknown we cannot calculate. So it is a degree of 1 indeterminacy of this beam. Similarly, if you have a continuous beam, like if you see this beam, so this beam you can recall. This may be, if you visit the university, you will find all the structures, all the beams are basically continuous beams. So here you have one column which is fixed, then you have here another column which is maybe roller, another column, and single beam is continuous in all the beam, all the base or all the spans. So these beams actually we call it is a continuous beam. So here, this is the indeterminate structure. Continuous beams are normally indeterminate in nature. Why? Because here you have three unknown because it is a fixed and support. Here you have roller one, here one, one, one. Like that in this structure you have 3, 4, 5, 6, 7, 7 unknown reaction, unknown forces, and you have only 3 equilibrium of equation. So we can't solve all equations using the normal equilibrium of equations. So in that case, we have to use another method, that is we call it compatibility conditions. So for example, if you consider this beam, this end is hinge, this end is also hinge, right? So you have two unknown here, here also two unknown. So four unknown you have and three equations. So three unknown you can compute using the equilibrium of equations. But one extra additional unknown will be there, which you have to employ the compatibility condition of this beam. So one compatibility condition, if you can write in this beam, then we can solve the additional unknowns. Similarly, if you have a fixed end, so this cantilever beam, left hand side is fixed, for example, right hand side also fixed. So in that case, you have three unknown here and you have three unknown here. So total you have six unknowns, right? And you have the three equilibrium of equations. So this beam is actually indeterminate with the order of 3, because 3 unknowns we can compute using the equilibrium equation, whereas other 3 we can't. So to solve this beam, solve in the sense we have to draw the bending moment diagram, shear force diagram, slopes, deflections at any point we calculate. So for that we need to first find it out the reactions, 6 reactions. So here 3, here 3. So equilibrium of equations we have 3. So 3 we can compute. Remaining 3 we have to write compatibility equation for this beam. So that compatibility equation will give us 3 more unknown reactions. So today we'll employ 3 moment equation to solve the indeterminate structure and continuous beams. So this is very much real problem, real life. If you see, all the beams are actually continuous beams, not in a single beam. Unlike this one, our real structures are actually continuous beams, and beams and the structure is also indeterminate, highly indeterminate in nature. But till now we discussed how to solve the determinate beam, that is simple structure. So today we'll employ 3 moment equation to solve a continuous beams. So how to do that? So why the equation is 3 moment here? So in this method, so see, this beam is a continuous beam, but in this method we'll consider only this portion. So from left hand side to right hand side. So 3 support we'll consider. Even 3 support also, if any structure has 3 support, that beam also will call it continuous beam. Right? So up to this and here, up to this also, if this beam is there, then also we'll call it as a continuous beam. If a span is more than 1, then it is continuous. So in the 3 moment equation, we divide entire continuous beams into 3 supports. So this is one continuous beam up to this. So from here, so again here you have another continuous beam. Like that we divide the entire continuous beam into 3 segments. And then we employ our equations. So if you consider, so this is another beam. So as I mentioned, so we'll consider this middle 3 portion. Any 3 will derive the equation, and these 3 will be replicating in the other portion of the beam as well. So let's derive our 3 moment equation now. So let's consider this portion, this beam, and these 3 supports we are coming. So these 3 supports are there, and some loads are acting, UDL, point load, whatever may be the combination of loads are acting. So because of this load, you will have the deflections. So this is a deflected shape of a beam. Okay, so and as this is a continuous beam, so there will be support moment also. If you recall, the roller support don't have any moment, right? Only fixed support has a moment reaction, whereas roller and hinge support don't have any support reaction. But if it is a continuous beam, then each roller support also have some moment. So here also you will find some moment. Here also moment is not zero. You will have some moment. Here also some moment will be there. So in all the points, all the roller support itself, you will get some moments, reaction moments. So you will have here, this is the roller support, you will have a moment here, ml for example. So each three we call it, this is the middle portion, we call it c, that is center support. Left side we call it l, and right side we call it r. So that's why the nomenclature. So this will be r, middle will be c, and this will be left l. So moment here in this support is we denoted ml, this is mc, and this is mr. Similarly length also, this is l, l, L is left, and this is LR. Similarly, if you draw the slope at this point C, so CL will be the slope left hand side and CR will be the right hand side slopes. So at this point basically we'll write our compatibility equations. So what is compatibility equation? As I mentioned here, to solve the indeterminate structure, anyway we'll get three equations from the equilibrium of equations. But remaining extra equations we have to derive it from the compatibility condition. What is compatibility condition? For example, if you consider this beam, this portion, this support I am talking. So after application of the load, the beam will buckle here. So the buckling, whatever will happen in this side, that is the slope here, theta CL and theta CR. So if you take, this is a roller support, right? So the net moment in this section should be equal to 0. Net moment in this section should be equal to 0. That means the net slope in this section should be equal to 0. So that's why theta c plus theta cl plus theta cr should be equal to 0. So this is our compatibility equation. Why it is 0? Because see, this is what? This is roller support, right? Roller support has 0 net moment. So net moment should be in this support should be equal to 0. So that's why the slope also, the summation of all the slopes at that point should be equal to 0. So that is our compatibility equation. So this is the main compatibility equation. So theta cl plus theta cr equal to 0. So now find it out what is the value of theta CL and theta CR. So how to calculate slopes? Already we saw using the geometric method, we know how to calculate the slope. So if you can employ moment area method or conjugate beam method, any method we can employ and find it out what is the theta CL and theta CR. So here we have employed the moment area method. As we know, it is very easy to calculate using the moment area method. So we'll do it. So theta CL will be what? Theta CL is here in this diagram. So as per the moment area, now let's do it here. So at this point, so here we have drawn a tangent. So this is a tangent at this point, right? So if you extend this tangent, so let's extend it, and if you write the here. So now at this point, now if we find it out, what is the deflection happened at L? So this is at L, left hand side, we call it L. This is center C, and this is R, already written R, right? So at L, whatever is the deflection, this delta I am talking. So this L. So what is theta CL? So theta CL is this angle. This angle. So this can be written as theta CL can be written as, if you take the triangle is what? Delta. Delta is the total deflection at this point and total length. So total length is given to us this L. So L. So that will give us theta CL. Right, from the simple geometry we can compute what is theta CL. That is this angle I am talking. This angle will be nothing if you consider this triangle now. So what is this angle? This angle will be simply height into base, that is tan theta, right? So theta CL equal to height is delta by total length. Total length already we know, L. So this is LL. So now that's what is written, deflection at L divided by LL. So what is the deflection at here at this point? So using the moment area method, we can find it out what is the deflection. So that is nothing but the m by that area under the m by ei diagram. If you take the moment of the m by ei diagram, that will give the deflection, right? That is our moment area theorem. So that's what. So moment of m by ei diagram. So this is the m by ei diagram for the loading, and this is the m by ei diagram for the end support reactions. So now find it out and replace the values. So here if you see the m by ei diagram, so this m by ei diagram is for this loading condition. So how much is the area inside? So area will be simply AL is given to us. So AL into, we have to take the moment. Moment means area into CG distance. So CG distance is XL. So that's why it's written AL into XL by EI, and this LL is there anyway, 1 by LL is there. So this is the first part came from this part. Now next momentary M by A diagram, moment will generate because of the support moment also. So this is the M by A diagram for the support moment. So here you have ML, MC, moment at C, and MR. So from here, basically we are finding out this entire area, left hand side, right? So this area means this triangle plus this triangle. So what is the area of this triangle? Half into base. Base is LL into height is ML by EI. So this is the area multiplied by the CG distance. So CG distance will be 1/3 of LL. So that's why 1/3 of LL. So this is this part. And now for this top triangle, what is the area? So area will be half into base. Again, base will be LL into height is now MC. And what is the CG distance? CG distance will be 2/3 from the LL, right? So it will be lying somewhere here. So it will be 2/3. So 2/3 from the LL. So this is our final expression for theta CL. So if you just simplify this entire expression, you will get this is the final expression for theta CL. Similarly, for theta CR also we can compute. So theta CR also can be done from this figure, and from this two triangle we will get theta CR also. If you do it, you will get this is the final simplified equation. So now substitute theta CL and theta CR. So theta CL value already we know this one. Similarly, theta CR value also we know. Just plug in the compatibility equation here. So both the values if you plug in, you will get this is our final expression. So from this expression, if you simplify, that is our final three moment equation. So this one is our final three moment equation. So you have to remember this three moment equation. Yeah. So three moment equation is nothing. Why it is called three moment equation? Because in this expression basically we are relating three moments. What are the three moments? One is middle moment MC, left hand side ML, and right hand side MR. That's why we call it, this method is three moment equation, because we are relating ML, MC, and MR, three moments, support moments we are relating, and the equation is written. So that's why this method is called three moment equation. So using three moment equation, we can compute all the unknown forces, unknown reactions in a beam, and we can draw the bending moment and the shear force diagram. So please recall this formula, please remember this formula. This is very much important, and that's how we derived. So what we did, we used the compatibility equation. Please remember, very much important. In reality, all the structures are actually indeterminate structures. Indeterminate structure means using only the equilibrium of equations we cannot solve this. Solve in the sense we cannot find the shear force diagram, we cannot find the bending moment diagram, we cannot find the reactions. So we need some extra equations to solve these indeterminate structures. So those extra equations we call it compatibility equations. So for example, here in this beam we applied one compatibility equation to find it out. So this is the compatibility equation, then we replaced theta CL and theta CR value, and we got our final expression, that is three moment equation. So now let's solve a example, quick example, then the problem will be very clear to you. So what is the question? A continuous beam A, B, C, D. So name nomenclature is not given. So this is A point, B point, C point, and this is D point, right? So this is a continuous beam. So more than one span we call it continuous. So even if only up to this A to B is a simple beam, when B to C again came means it is a continuous beam. More than one span means it is a continuous beam. So a continuous beam of ABCD carrying a uniformly distributed load, of 1 kilonewton per meter. So UDL is acting 1 kilonewton per meter over the span, in addition to the concentrated load. So in addition, the concentrated load is already acting here 10 kilonewton. In addition to that, unit load is also acting. So calculate the support reaction. Also draw the bending moment and shear force diagram. So what you have to do, you have to find out all the support reactions, and you have to draw the bending moment and shear force diagram of this beam. Assume that ABC is a constant, that EI for ABC is a constant for all members. So very simple. So you have to find out all the support reactions first, and you have to draw the bending moment and shear force diagram of this beam. So you can recall this is a very real beam, real structure. So multiple, beams are continuous in multiple supports. So now let's find whether, first check whether this beam is determinant or indeterminate. As we know, all the continuous beams are actually indeterminate beam. So let's verify whether these beams are determinant or indeterminate. So here you have what? Hinge end, right? This is hinge support. So hinge support has how many unknowns? Hinge support has two unknowns. So at A you have two unknown. Similarly at B also roller. Roller means you have only one unknown. Similarly at C also you have one unknown. So total how many unknowns? So we have four unknowns. And how many equilibrium of equation we have? So we have three equilibrium of equations. So that's why this beam, this continuous beam, is a indeterminate beam with a degree of 1. 1 is unknown, so that's why 1 with a degree of indeterminacy of this beam is 1, and this is an indeterminate beam. So now let's employ our three integration method to find it out, all the reactions first, and then we'll find it out the bending moment and shear force diagram. So what are the reactions? Here you have through two reactions. So here you have one reaction and here you have one reaction. So all the RA, RB, RC, all values we have to find it out. So now in the three moment equation, if you recall, we last slide we saw there was MC at the middle support, we call it MC, and right hand side is MR and left hand side ML. So using these three equations, we have derived the three moment equation. So here, what is the moment here at MC? Right hand side, what is the moment here? So this moment, by inspection only we can tell what is the moment. So moment will be simply force into distance, because here it is a cantilever portion. So force is how much? 5 into 3. So MC at this point is 15, because 5 into 3. Here at this point moment is 15. By inspection only we can find it out. Similarly, at this point A, so A is what? This is the roller hinge support, right? So hinge support means the reaction moment will be 0. So MC already we know 15, and MA also we know 0. Now we have to find out what is the value of this part, middle portion, that is MB. MB is unknown to us. So we employ the three moment equation. Last slide you saw the three moment equation where ML was here MA, which is nothing but 0, and MR right hand side moment, here it is 15 given to us, and middle MC basically we have to find it out. Here it is MB. So just plug in all the values and you will get it what is the value of MB. So MB is this much. So all the reaction that AR XL from this moment diagram we have to draw, we have to find it out all the values. Once you plug in all the value, we will get final MB equal to 18.125. So moment at B is now 18.125. Now our main objective is what? Calculate the support reaction. We have to find out support reaction. RA, RB, that is vertical RB, RC, and then shear force bending moment. Everything we have to draw. So anyway, we calculated what is MB, that is moment at this support is minus 18.125. So now we'll find it out other parameters. So now this entire beam is now divided into two parts. So this is the left part and this is the right part. At B we already computed that is 18.125. It is not 17. Just change the value. This is not 17. This is the wrong value. Just now we computed this is 18.125. Just make the correction. This is not 17. It is 18.125. So moment at B we computed 18.125, and we just splitted the structure into two parts. Now find it out what is RA from here. So use equilibrium of equations first. So take moment about B equal to 0 and write down what is RA. RA into total distance. So RA into total distance is 10, which is clockwise direction. That's why you consider it positive. Then you have another force is acting, that is 10 kilonewton, which is acting anti-clockwise direction. So this 10 kilonewton is acting anti-clockwise direction. That means it is negative, but 10 into distance is 5. So this distance is 5 given to us. And then you have the UDL is also acting. UDL is 1 kilonewton per meter. UDL is acting. So WL square by 2. If you employ, you will get minus 10 into 5. From UDL it is coming. And then you have the moment also. Moment is 18. So here at this point, so 18 is a moment, 18.125. So 18.125 equal to 0. So from here we can calculate what is the reaction RA, which is nothing but 8.1275. Now similarly, just find it out what is RBL. RB has two portions, right? RBL and RB right. RBL and RB right. So that will be simply total load minus RA. So total load is how much? Total load is 10 kilonewton acting plus UDL is also acting 10. So 10 plus 10, 20. 20 total load acting downward. RA is taking 8 point something. Then what RBL will take? So this 20 minus 8.1875. So whatever value we'll get, that is nothing but 11.8125. So that is our RBL. Similarly, for this diagram, from the right hand side diagram, find it out. Same process. What is RC? Take moment, similar moment you write. Find it out what is RC. RC value is this much. Find it out what is RBR. That is this much. So once you know all the support reactions, now you can easily draw the bending moment and shear force diagram. So this is a shear force diagram. How we have drawn. What is the reaction at A? Reaction at A is 8.1785. So that's why from A we go up positive 8.1785. Same. Then you have UDL is acting downward. That's why downward slope is coming. When you reach to 10 here, 10 acting downward again. So at this point again you go 10 downward. You will reach here. Then again you have the UDL going. So again UDL means this inclined line will be coming. So when you reach at B, so B means what is total B? Total B will be 11.8125 plus B left plus B right. So 11 plus 5. So it will be 16 point something coming, right? 17.2 something. So from here at 17.2 something, you will come here. Then again you have the UDL is acting. So UDL means again go down. At point C, again you have the RC value. RC value is 4.75. So RC value you reach here. Okay, then you have the 0 at this point you have 0. So this is our shear force diagram. Similarly, bending moment diagram also it can be drawn. What is the bending moment at this point? This is the hinge and support, right? Hinge and support means 0. So that's why it starts from 0. Then it is UDL, right? UDL is acting. So UDL acting means you will have a parabolic shape, and then at C, at B, at middle portion already we know it is 18.12 MB we computed. So that's why it is 18.12. Again you have the UDL is acting, so ultimately minus 15, and this is the bending moment diagram of this beam. So that's how we completed using the three moment equation how exactly we can solve the shear force and bending moment diagram. So we use the compatibility equation to find it out the extra reactions, and then we have computed all the unknown reactions, and we drawn the bending moment and shear force diagram. So that completes our how to analyze the structural analysis in a continuous beam. Thank you.